Okay, in section 1-2, we're going to review functions and their graphs. So, the first thing we'll talk about here with functions and their graphs is kind of, first of all, what is a function? And a function is a relationship, a rule that we set up between a set D, which of course stands for domain, to a set R, the range. And it's this rule or relationship where you assign a unique element, one element in the range for every element in the domain. So just to use a visual to kind of remind you of how this works, the picture on the left shows a function while the one on the right is not. A function is such that the relationship where every value in the domain, every x value, we usually think of it as x, not always, but every element in the domain gets matched up just once with an element in the range. Now, notice it is possible for two different x's, two different elements in the domain, to be matched up with the same value in the range. That's fine. That is still counted as a function. But what you need to have is that each x, each number here on the left, can only go to one number on the right. It can't go to multiple. And that's where, if you look at the second picture, this is not a function because this element in the domain is getting matched up with two separate values in the range, and that makes it not a function. When we have a function, then we will use function notation. So that's an example of function notation. Remember, we just take out the variable y, and in its spot, we put f of x. And it's just that f of x stands for the y value when you're plugging in x, so you can write things like f of 2. And when you write f of 2, what you're saying is, if I say f of 2 equals, well, in this case, what would it be? F of 2 equals negative 2. What we're saying is that the y value is negative 2 when our x value is 2. Now, some ways, just kind of ways of speaking, vocabulary here. When we say, for example, that temperature that water boils is a function of elevation, what we're saying here is that the temperature depends on the elevation. The temperature that water boils at will depend on the elevation. It's a function of the elevation. So we can write that as a function here. Temperature is a function of, so instead of using f of x, we might use t for temperature. And when we say a function of elevation, that means your elevation would be the variable that goes in. You'd have some equation in here, but there would be, oops, not an x. It's a function of elevation, so we'd have e in there of some sort, and I'm not talking about the e that's on your calculator, the irrational number, but just e is a variable here for the elevation. And you'd plug in the elevation if you want to know, like in Denver, Colorado, plug in the elevation and you would know what temperature the water would boil. You can also say that the area of a circle is a function of the radius. What we're saying is that for any circle, its area will depend on what the radius is. If you have a larger radius, you'll have a larger area. Once you know the radius, you can calculate the area using this function. So again, area is a function of, so we say area, right, instead of f of x, area, and then it's a function of radius, which just tells you that the radius will be the variable, and it will appear then in your equation for the function. All right, unless it's stated otherwise, the domain for the functions we will look at will be assumed to be the largest set of x values you can come up with that then give you real y values. That's what's called the natural domain. Now, just to review kind of with you how to write intervals here using interval notation, we can say, for instance, that the domain is all real numbers. And you've seen it here with inequalities, right? And then you've also seen this in pre-calc where we use the parentheses and the brackets. So going from negative infinity to positive infinity, don't forget we use the parentheses with infinity because you can never actually reach infinity. Over here on the right, here we're saying the domain is all values that are less than b but not counting b. You can see that with that open dot. So b is not one of the values included. And so then again, we can write it, notice the parentheses showing that b is not included. It's everything up to b, but not including b, and then going to negative infinity. And we can look at other examples here. The one on the left here, we're looking at all values that are greater than a, so again, using the parentheses there. On the right, the difference here now is that we're saying less than or equal to b. b is included. So with inequality, you write it as a less than or equal to sign. Here, we would use a bracket to show that b is included, but notice you still have the parenthesis for negative infinity. A couple other examples here. My computer goes slowly. Here we're saying all values between a and b, but not including them. Once again, we have the parentheses showing that. Here we're saying all values between a and b, but a is included in the domain. Notice again the bracket there on a, but then the parenthesis on b. And I think there's a couple last ones here. Here we have the closed interval from a to b, meaning that both a and b are included. You'll notice we have brackets on both ends. And then this last one shows that b is included but not a. So those are just different examples. Again, this is just reminding you of how you can write that. So now let's talk about even functions and odd functions. Here's the definition. An even function is one such that if you plug in an x and if you plug in a negative x, you actually get the same y value. And it happens not just once, but for all x values. So if you plug in 8 and negative 8, you plug in 2 and negative 2, you plug in 9 and negative 9, you plug in decimals. All of those, we always get the same y value. That makes it an even function. So again, when you look at the notation, f of negative x, we're saying that's the y value you get when you plug in negative x. And f of x, that's the y value you get when you plug in x, and we're saying that they are equal. So that's an even function. An odd function is one where if you plug in an x and plug in a negative x, you don't get the same y value, you actually get opposite y values. And you can see that right here with that negative sign. Let me get rid of all this stuff here. We're saying that f of negative x, that's the y value you get when you plug in negative x, and f of x, they're not equal, they're opposites, and you can see that there with that negative sign. And again, it doesn't just happen at one point, but happens at all points. And if we look at a graph example of each of these, the one on the left shows an even function. It's our standard parabola. And if you plug in a point like, let's say, 1, you of course get 1. If you plug in negative 1, you also get 1. But it doesn't just happen there at 1, it happens at 2, then you're up here at 4, and you plug in negative 2, and again you're up here at 4. And it happens everywhere. They're showing that here with just a generic xy, that's always going to be matched up with negative x, so the opposite x value, but the same y value. That's an even function. Now, you can tell you have an even function by looking for some symmetry. Even functions are symmetric by reflecting them over the y-axis. So if it is symmetric by reflection over the y-axis, it's an even function. If you look over on the right-hand side, this is an example of an odd function. If you look at this point here, it's x, y, and then when you plug in the opposite of x, negative x, you get negative y. And that happens for all points. Now, it is possible, it doesn't have to be where you have a positive x and a positive y. It could be that you have a positive x and a negative y. So you might be down here in the fourth quadrant, and then when you plug in the negative x, you'd get a positive y, so it'd be up here. So it can happen either way, but you do need to know that when you plug in an x and then the negative x, you do get opposite answers, one positive and one negative. The symmetry that's going on here, it's not a reflection, it's a rotation. It's a rotation around the origin of 180 degrees. So if you can rotate that graph 180 degrees and have it look the same, that would mean that you have an odd function. Here, let's take a look at an example. And we can certainly graph these. The first one is actually the first graph we just looked at there. That's the standard parabola. It is symmetric to the y-axis, and you can also just think about it. If you plug in an x and then square it, and then you plug in the same number but negative and square it, you will, of course, end up with the same answer. What about the second one? Well, if we plug in an x, we're going to get x squared plus 1. If we plug in a negative x, well, we would get negative x squared plus 1. But when you square negative x, you'll get x squared plus 1. So notice we get the same answer for both. So again, that would be an even function. You could also graph this one on your calculator and see that it's symmetric by reflection over the y-axis. If we look at the third one, if I plug in x, well, I get x. When I plug in negative x, I get negative x. And so you'll notice that we get opposite answers, which tells me that this is an odd function. That's just your standard 45-degree line. And if you think about that, that's symmetric by rotation, 180 degrees around the origin. Now, you might think with this fourth one, it's just like what we happened up above, that by adding 1, it's still an odd function. But it won't be here, because when I plug in x, I get x plus 1. And when I plug in negative x, I get negative x plus 1. Those are not opposite answers. The x's are opposite, but they both have a plus 1. And if you just try a number, you'll see. If I plug in 4, I get 5. When I plug in negative 4, I get negative 3. So those are not opposite answers. And so it's neither odd nor even. Piecewise functions. You've seen these before. They can be lines, they can be quadratics, they can be any sort of things, and they're pieced together. So if you would need to graph one of these, usually what we do is we make a little table, x and y. I know for this first piece, it's for all x's that are less than 0. So I would probably plug in 0 and get 0. And then I want to plug in something less than 0. I plug in negative 1. And when I plug negative 1 into that, I'm actually going to get positive 1. And maybe I do it one more time, plug in negative 2, and I would get positive 2. And I know from this that this is going to be a line. It's going to be a line with a slope of negative 1 and intercept of 0. And I can see that, oh yeah, here's my y-intercept right there at 0, 0. Now I would need to put an open dot there because I know that technically I can't plug in 0 into this function, so it's everything up until that point. And then at negative 1, I'm up here at positive 1, and at negative 2, I'm up here at positive 2. So the function's going to go off like that in that direction. So that's the first piece of my function. And then I could keep doing the same sort of thing. For the second part, I would need to plug in values between 0 and 1, including 0 and 1. And I know it's going to be part of a parabola. So if I make my table here for the green part, when I plug in 0, I get 0. When I plug in 1, I get 1, and I know it's going to be a curve this time. Well, 0, 0 actually fills in this dot from before. So that point wasn't there because of the first one that we did, but for the second part. And then at 1, I'd be at 1. But now this one won't be a line because I know the shape of this function. So I'd actually have a sort of curve here. And then for the last part, I would be plugging in values into this here, but it's 1. It's always 1, no matter what I plug in. So for all x's that are greater than 1, I'm going to be at 1. So that means if I were to make a table, once again, now I would start at 1 because it says x greater than 1. I just have to do an open dot there. So at 1, I would be at 1. And 2, I would be at 1. At 3, I would be at 1. This is going to be a horizontal line. And technically, I would put an open dot here at 1, but it's already filled in because of the previous part of the function. So sometimes your piecewise will match up like that. So that's actually going to be a filled-in dot, and then I'm going to have a horizontal line going off in this direction. And I have a little bit nicer looking graph here, which is showing basically what I just had. You have the line here, then we have the part of the parabola there, and then the horizontal line going that way. So that's an example of a piecewise function. Absolute value function. You probably recall that when you graph an absolute value function, that it looks like a V-shaped graph. When I plug in 0, I get 0. Plug in 1, I get 1. 2, 2, 3, 3. It continues on in this direction. When I plug in a negative 1, I get positive 1 because of the absolute value. Plug in negative 2, I get positive 2. And this continues off in this direction. And I get that sort of graph. Now, when you first learned about absolute values, you were probably shown this, that you can actually think of the absolute value function as a piecewise function. If you look at the first part, we're saying that x equals the opposite of x, and that's when x is negative. If you think about when I plug in negative numbers into an absolute value, it doesn't stay negative, it becomes the opposite of that, it becomes positive. And then the second set here is saying that you just get the same value, whatever you plug in, that's your answer for anything that's 0 and above. And so here's the same graph. I grabbed this out of our book, and you can see the two pieces. This left-hand part is the first part of the piecewise function, and then this green part here is the second part. So that's the green part, that's the red part that's graphed down below. All right, and then lastly, talking about composition of functions. You will recall f of g of x. This is taking and kind of placing one function inside of another. This is evaluating the function g first. We start on the inside and work our way out, and then plugging that value into the function f. You'll also see it written this way with the little open dot there, that composition. That's saying the same exact thing. And then over here on the right, we have kind of a picture, diagram showing what's going on here, that you're going to start out with some value x, plug it first into the function g. So that's the important part out of all of this, is to remember that when you have a function like this, or a composition of functions, I should say, that g is actually the one that we work with first, that x gets plugged in to g first. And again, when it's written this way here, g is the one that we operate on an x first, and then take that answer, and then lastly plug that into f. And so you can see that here on the right, that after we plug it into g, out pops g of x, but then that gets plugged right away into the function f, and out pops our final answer. That's a composition of functions. So just as an example here, if we're given two functions that g of x is x squared and f of x is x minus 7, I know the question only says find f of g of 2, but let's actually find f of g of x first, and then we'll find f of g of 2. So f of g of x, which could also be written like this. When you want to find an equation for this new function, this composition of two functions to kind of create a new function, we're going to start with g. G is x squared, and so we're going to plug that into the function f. So f, I just write the letter f because I haven't done anything with it yet. And then in place of the g of x, or in place of the g of x, I'm going to put x squared. So that's going to go inside of that parentheses there. And now I'm going to go to the function f, which is right here, and I'm going to take out this x, and in its spot, I'm going to put what's in the parentheses, which in this case is x squared. So now I'm going to have x squared minus 7. And that would be my new function for f of g of x. Now, when they ask us to find f of g of 2, there's actually two ways to do it. Since I've already done the work to find f of g of x, I could just go ahead and plug in 2 right here into our equation. So I would have 2 squared minus 7, which would be negative 3. Now, if I hadn't done all of that work, let me go through and show you how we could do this kind of from scratch. If I was asked to find f of g of 2, we should get the same answer, but in a slightly different way. I'm just going to copy the letter f out front because it has to wait its turn. And we're going to evaluate this inner part here, this g of 2. So I'm going to plug in 2 into the function g. Let me clean this up a little bit. So I'm going to plug in 2 into the function g right here, and I get 2 squared, which is of course 4. And now I'm going to plug in 4 into the function f, so then I come up here and plug in 4, and you'll kind of recognize we sort of already did this, we just did it in one step. 4 minus 7, we get negative 3. So we get the same answer for f of g of 2, two different ways. In the first way, we found the equation first and then plugged in our value of 2. In the second one, we just started with one equation, got that answer, and then plugged that answer into f, which is really an example of this diagram that I showed you up here at the beginning of the page.